In this video, you're going to learn how to compute improper integrals. An improper integral is an integral that has a bound at infinity, like this one here, the integral from 2 to infinity of 1 over x squared dx. Now, your first question might be, what does this even mean to have a bound at infinity? And the answer to that question is that the integral still means the same thing as usual. It means the area under the graph, in this case the graph of 1 over x squared. And to be precise, the area that we want runs from the x-coordinate of 2 to the x-coordinate of infinity. X-coordinate of 2 might be somewhere here on the graph, kind of close to the y-axis, and x-coordinate of infinity means we want to go infinitely long in the x direction. So it's basically all the area that's on the right side of 2 going towards infinity. So yes, that's right, this integral represents the area under an infinitely long curve. And because it's an infinitely long curve, you might just think that the area is infinite. But just to make sure, why don't we go ahead and evaluate this integral the long way? You might be in for a surprise. Now, to evaluate this integral, we have to be a bit more precise. What we really mean when we say the integral from 2 to infinity is we mean the integral from 2 to some bound b, but we're taking the limit as b approaches infinity. So again, what infinity means in an upper bound is it's the limit as the upper bound approaches infinity. So the integral from 2 to b of 1 over x squared dx, that looks pretty familiar. 2 and b are just constants, and this is a proper integral. We know how to compute it. So why don't we go ahead and do that? We'll compute the integral. This integral is easiest to compute if we write it as x to some power. 1 over x squared is just x to the negative 2 power. So we're taking the limit as b approaches infinity of the integral from 2 to b of x to the negative 2 dx. And using the power rule for integrals, all we have to do is increase that power by 1. Negative 2 plus 1 is x to the negative 1, and then multiply it by the reciprocal, but the reciprocal of negative 1 is just negative 1. So negative x to the negative 1, evaluated at the bounds 2 and b, take the difference, and also take the limit as b approaches infinity. Just to make the notation a bit friendlier, let's convert this x to the negative 1 back into a 1 over x. So it'll be limit as b approaches infinity of negative 1 over x from 2 to b. And then we'll go ahead and plug in the bounds, take the difference. So it'll be the limit as b approaches infinity of, plugging in the top bound b, negative 1 over b, then minus, plug in the bottom bound, negative 1 over 2. And we'll simplify, that's just the limit as b approaches infinity of negative 1 over b plus 1/2. But the limit as b approaches infinity of negative 1 over b, that's negative 1 over an increasingly large number. It's like negative 1 over infinity, which is just 0. So 0 plus 1/2 is the result, and 0 plus 1/2 is just 1/2. That's an actual finite number. But that's supposed to represent the area under an infinitely long curve. Can that actually come out to a finite number? Does that make sense? Well, yes, that is truly the answer. We did not make any mistakes along the way. That is actually what it is. The area under this infinitely long curve from 2 all the way to infinity is 1/2. That's right. So the takeaway here is that the area under an infinitely long curve can actually be finite. And in such a case, when an improper integral like this one here comes out to a finite number, we say that the integral converges. Now, before we go on, I understand if you might be unsettled by the fact that the area under an infinitely long curve can be finite. And I think it might put you at ease to remember that the sum of infinitely many numbers can still converge to a finite number. You may have already seen the geometric series a half plus a fourth plus an eighth plus so on. And the fact that this series converges to 1 is a bit more familiar when you think of it in terms of eating a pizza. If you eat half of the pizza to begin with, and then you eat a fourth of the pizza afterwards, and then you eat an eighth of the pizza after that, and then a 16th of the pizza, and so on, it's like you're always eating half of what's left. So you can never actually eat the whole pizza. But as you keep on eating half of what's left, you get really, really, really close to eating the whole pizza. In fact, if you think of any number that's less than 1, like 0.99999, you would eventually eat that much of the pizza. So the amount of pizza you eat approaches the whole pizza as you take infinitely many bites. So hopefully this makes you a bit more comfortable with the idea that an improper integral representing the area under an infinitely long curve can actually converge to a finite number. Let's try some more examples of computing improper integrals. Consider this one here, the integral from negative infinity to 1 of e to the x dx. This time the infinity is in the lower bound and it's a negative infinity. But really the process remains the same. What we mean by this integral here is we mean the limit of the integral as the lower bound tends to negative infinity. So why don't we call the lower bound a, and we'll say that this integral is equal to the limit as a approaches negative infinity of the integral from a to 1 of e to the x dx. So now we've got a nice proper integral that we can solve pretty easily, and then we'll just take the limit. The antiderivative of e to the x is, well, just e to the x. It's just itself. And that's being evaluated at the bounds a and 1, and we're still taking the limit as a approaches negative infinity. So that's the limit of the difference at the bounds. At the top bound, we've got e to the 1, and then at the bottom bound, e to the a. E to the 1 is just a constant, so it's not affected by the limit. It's still e to the 1, which is just e. And then e to the a, the limit as a approaches negative infinity, is 0. E to the negative infinity is like 1 over e to the infinity, which is 1 over a really big number, infinity, and 1 over infinity is 0. So here we have it, e minus 0, e. That is the value of the improper integral. It's another one that comes out to a finite number. So again, we say that this integral converges. Now, although we've worked two examples where the improper integrals both converged to a finite number, this isn't always the case. Let's illustrate with another improper integral, the integral from 5 to infinity of 1 over x dx. At this point, we're pretty familiar with the process used to evaluate these integrals. This is just the limit of the integral where the upper bound tends to infinity. So limit as b goes to infinity of the integral from 5 to b of 1 over x dx. Remember, the antiderivative of 1 over x is natural log of absolute value of x, and we're going to be evaluating this at the bounds from 5 to b and taking the limit as b approaches infinity. So this is the limit as b approaches infinity of natural log of absolute value of b. Well, b is a positive number because it's tending towards positive infinity, so we can just write natural log of b, and then minus natural log of the absolute value of 5. And 5 also a positive number, so its absolute value is just 5. Now, natural log is an unbounded function, meaning as the input gets bigger and bigger and bigger, so does the output. So the limit as b approaches infinity of natural log of b is infinity. Natural log just keeps growing without bound. And then the minus natural log of 5 just stays the same. It's a constant, so it's not affected by the limit. And if something's tending towards infinity and you subtract some constant from it, well, it's still going to be tending towards infinity. So that is the result, infinity. The area under the curve 1 over x, where x goes from 5 to infinity, is truly infinite. And because of that, we say that the integral diverges. And in general, we say that an improper integral diverges whenever its limit doesn't exist. A limit going to infinity is a special case of a limit technically not existing, because there is no finite number which the limit approaches. We'll illustrate this with one final example. Consider the improper integral from 0 to infinity of cosine of x dx. Of course, we know that this is the limit of the integral as the upper bound, call it b, tends to infinity. So we'll write that integral again, but this time with an upper bound b, and that way we can actually evaluate the integral in terms of b. The antiderivative of cosine is just sine, and that's being evaluated at the bounds from 0 to b, and we're taking the limit as b approaches infinity. So this is the limit as b approaches infinity of sine of the upper bound b minus sine of the lower bound 0. And sine of 0 is just 0, so really this is just the limit as b approaches infinity of sine of b. But as b approaches infinity, sine of b doesn't settle down to anything. It just keeps oscillating up and down and up and down and up and down. So this limit does not exist. And because that limit does not exist, the improper integral, once again, diverges.